this video, we will be discussing about divide nodes into the maximum number of groups. You are given a positive integer n representing the number of nodes in an undirected graph. The nodes are labeled from 1 to n. You are also given a 2D integer array edges where edges of I equals to ai bi indicates that there is a bidirectional edge between nodes ai and bi. Notice that the given graph may be disconnected. Divide the nodes of the graph into m groups one indexed such that each node in the graph belongs to exactly one group. For every pair of nodes in the graph that are connected by an edge aibi, if ai belongs to the group with index x and bi belongs to the group with index y, then the absolute difference between x and y is equals to 1. Return the maximum number of groups, that is maximum m, into which you can divide the nodes. Return -1 if it is impossible to group the nodes with the given conditions. So what they are saying is that in the input we are given n, which denotes the number of nodes in our graph, and we are given the edges vector. So there are n nodes which are labeled from 1 to n, and these are the edges between those nodes. This is a unidirectional graph. So the edge between 1 and 2 denotes that there is a bidirectional edge between node 1 and node 2. Right. Now what we need to do is that we need to divide this 6 nodes into some number of groups such that we maximize those number of groups, right? And whatever is that maximum number of groups, that we need to return as our answer, right? So now when we are dividing our nodes into some number of groups, there are some conditions that we need to follow. So the first condition is that each of the node should be present in exactly one group, right? Basically, a node cannot be present in two groups, right? Then the second condition is that wherever there is an edge between two nodes, then the difference between their groups should be equals to 1. So basically, if these are the two nodes and this belongs to group 1, then the node which is connected to this node with an edge, it can either belong to group 0 or to group 2. Basically, the absolute difference between the groups of these two nodes should be equals to 1. Right? So that is what they are saying. These are the conditions that we need to follow. And following these conditions, we need to maximize the number of groups that we can form. Right? So with these edges, I have formed a graph over here. Now with the help of this graph, if we try to put the nodes into different groups, then what can we do? So this is node 5, right? We can keep it in group 1, right? Then 1 is the adjacent of 5. So either it can be in group 0 or group 2. Let us suppose we give it group 2. Then node 2 and node 4 are adjacent to 1. They share an edge with 1. So they have to be either in group 1 or group 3. Right? So we are having two choices, group 1 and group 3. If we keep node 2 and 4 in group 1, that will work, but we want to maximize our number of groups, right? So we will give them group 3, right? Then 3, it is sharing an edge with 2. So it can either be a part of group 2 or group 4. So we will keep it in group 4, right? Then 6 is sharing an edge with 2 and 4. 2 and 4 are part of group 3. So it can either belong to group 2 or group 4. So let's suppose we give it group 4, right? So how many groups we have created? 4. Right? And 4 is the maximum number of groups that we can create, and this is our answer, right? So now, if let us suppose that I consider this as my starting node, right? Now I keep this in group 1. So now 5, 2 and 4, these are sharing an edge with node 1. So they can either be in group 0 or group 2. So let us suppose I keep them in group 2, right? Then 3. 3 is adjacent to 2, so it has to be either in group 1 or group 3. I will keep it in group 3 because I want to maximize my number of groups. 6 is sharing an edge with 2 and 4. 2 and 4 are part of group 2. So it can either be in group 1 or group 3. So let us suppose we give it group 3. So now the total number of groups that we got from here is 3. Earlier when we started from node 5, it was 4. But from node 1, it is 3. And we will check for other nodes, then it will be some different number, right? So this is one observation that we have made, that when we start from a different node, we get different number of groups, right? So we will keep this thing in mind and we will use that later, right? So now the question also asks us that if it is impossible to form groups of all these nodes with the given conditions, then we need to return a -1. So now let us identify that what are those conditions in which our answer will be -1. So see, if let us suppose that I have a graph something like this, right? So now here, this is my node. I kept it in group 1. Now this node is adjacent to it, so I kept it in group 2. Now if you see this particular node, it is adjacent to this and adjacent to this. If we check for this one, then it can either be in group 0 or group 2. And if I check for this one, then it can either be in group 1 or group 3. So for this node, I won't be able to put it anywhere. Why? Because if I give this node a group 2, then for these two it is okay. But now here the difference became 0, right? But the difference has to be 1. So then that means for this graph, my answer is going to be -1, right? So from here, looking at this graph, you might think that if there is a cycle, then my answer will be -1. But no, if you see here also we had a cycle, but here we were able to form 4 groups, right? So let us consider another scenario, that let us suppose that my graph is something like this. Now here, this node I will keep in group 1, then these two are adjacent, so I will give group 2, then these two are adjacent, I will give them group 3, and to this one I will give group 4. So this is a valid split of groups, and then all the conditions are also satisfied. Here also we had a cycle, but we are able to form it. Here we were not able to form it, but here we are able to form the groups, right? And if let us suppose that our graph looked something like this, then in this particular case, what would happen? We would give group 1 to this, and for these two, we would give group 2, and to these two, we would give group 3. But then because of this edge, we are not able to have them either in the separate group or in the same group, right? So the conclusion that we can make from here is that if you see here, our cycle length was 3, here it was 6, and here it was 5, right? And here it was 4. So whenever our cycle length is odd, in those cases we are not able to form the groups, and in those cases our answer is -1. And wherever the cycle length is even, in those cases we are able to form, right? So this is the conclusion that we have made, that if we have an odd length cycle, in that case our answer is -1, right? And this we can identify with the concept of bipartite graph, right? So with bipartite graph, what do we do is that we take a node and we start DFS or BFS from that node, and we give some coloring to that nodes, right? So we consider only two colors, let's suppose 1 and 2, and with the help of that we identify whether we have an odd length cycle or not. So if we consider this particular example, so as I said, we will give color to the nodes on the basis of some condition. What is that condition? That if there are two nodes which are joined with an edge, right? This node is having a color of 1, then this node cannot have the same color. It should have the opposite color, which is 2, right? Then if there is one node connected here, so this node is connected with this node. So this should have a color which is different from this. So we will give it a color of 1, right? So that is what we do. So in this particular case, what can we do is that initially we can keep the color of all the nodes as 0, right? 0, 0, 0, 0, 0, 0, right? Then to the first node, we can assign a color of 1. So the nodes which are adjacent to this, we will give a color of 2 to these. How do we identify the color? So basically what we do is we do 3 minus whatever is the current color. Basically the color of the node which is adjacent to it. So here we have given a 1. This node is adjacent to this node. Its color is 1. So the color that we'll give to this node will be 3 minus 1, that is 2. Right? So we'll give 2 to this, and here also we will have 2. Then for this particular node, what we will do? 3 minus 2. 3 minus 2 will be 1. So we will give a color of 1 over here and color of 1 over here. And then here we will give a color 2 because of this node. And when you will check from here, again here also, this node is already colored, right? When you will check for this particular edge, then this node would already be colored. But ideally, its color should have been 2 if we consider this edge. And it is 2 only. So then that means this is okay. In this particular case, we can form the groups, right? But if we check here, so initially all the colors will be 0, right? Then to this node, we will give a color of 1. Then here we will give a color of 2. Here we will give a color of 2. Then to this particular node, with the help of this edge, we will give a color of 1, right? And to this particular node, with the help of this edge, we will give a color of 1. Then if we check this particular edge, now according to this, one of them should have been a 2, right? Both of them are already colored and both are having 1. But one of them had to be a 2. So then that means in this particular case, our answer is going to be -1, right? So this is how we can identify whether our answer will be -1 or not, right? But If it is this particular case, when our answer is not -1, then how are we going to identify that what is the maximum number of groups that we can form? So let's look at that as well. So now in the question, it is mentioned that our graph can be disconnected, right? So basically we have multiple connected components. One component is this, then there is one component, and then we have another component, something like this, right? So this could be our graph, right? So now since we want to maximize our number of groups, what we can simply do is that we can identify that how many maximum number of groups can be formed for these nodes, or basically for this connected component, right? Then what is the maximum number of groups that can be formed with the help of the nodes which are part of this connected component, and what is the maximum number of groups that can be formed with this particular component. And then we can add all these three, right? Whatever is the maximum number of groups that we are getting for all these connected components, we can add all of those and that will be our answer, right? So now how are we going to identify that what is the maximum number of groups that we can form out of a single connected component? So as I said, when we looked over here, that when we were starting our BFS with a particular node, it was giving some number of groups. When we started with a different node, it was giving some different number of groups, right? So how we will identify that what is the maximum number of groups? So see, the constraints of the problem are very less. So what we can do is that whatever nodes are the part of these particular component, we can apply BFS for each of the node, right? So basically, this is one component, right? This is one connected component. These are all the nodes which are part of that component. So what we can do is that first we can consider this as our starting node and apply BFS. In the next iteration, we can consider this as our starting node and apply BFS. Then in the next iteration, this one, then this one, then this one, then this one, and so on, right? And for all of these, we will identify that what is the number of groups that we are getting, and we can just take the max of it, right? That if we consider this as our starting node, then what is the number of groups that we are getting? If we take this, then what is the groups that we are getting? And we will take the max of all of them, and whatever will be that max, that will be the maximum number of groups that can be formed with the help of this component, right? So now how are we going to identify that if I am considering this node as my source node, then what is the number of groups? So see, as it is mentioned in the question that if two nodes are connected with each other with an edge, they have to be part of a different group and their difference also has to be 1. So we will apply BFS from this node and we will try to identify that what is the distance of the farthest node from this particular node, from our starting node, right? So basically what we will do is we will give a distance of 1 to our starting node, right? Then we have 1 connected to it, so this will have a distance of 2. Then with 1 we have node 2 and node 4 connected, so we will give a distance of 3 to them, right? Then 3 is connected to node 2, so its distance will be 4. 6 is connected with 2 and 4, distance is 3 over here, so this will have a distance of 4, right? So the maximum distance that we have got over here is 4. So then that means if I consider this as my starting node in the PFS, then the maximum number of groups that can be formed is 4. Why? Because this will be part of one group, this will be one group, this will be one group, and this will be one group, right? But if I had started with node 1 as my source node, in that particular case, this would have a distance of 1. Then 5, 2, and 4 are connected with 1, so they would have a distance of 2, right? Then 3 and 6 are connected with these, so they would have a distance of 3. Here the maximum distance that we have got is 3, right? This is one group, then this is one group, and this is one group, right? So here I got the number of groups as 3. So that is the reason we will take the max of all the groups in this component, right? So basically, overall what we will do is that first of all, we need to check that for each of the component, is there any odd length cycle in that particular component or not, right? So we'll take this component, we will apply DFS or BFS and the concept of coloring to identify whether there is an odd length cycle or not. And when we are doing that, since we are applying DFS or BFS only, what we will do is that in a vector, we will push all these nodes. Why we will push all these nodes? So that somewhere we know what are all of the nodes which are part of this component, and then we can take this entire component, because in the vector we are having all the nodes, right? So for that vector we can apply BFS considering each of the nodes as our starting point, right? And then we will check for the next component. So if any of the component is having odd length cycle, we will simply return a -1. Otherwise, we will keep on checking, right? So when we will look at the code, you will be able to understand better that how are we going to apply all the different concepts here. I know it's a bit hard problem, but let's try to understand. So first of all, over here, we have created some global variables. Basically, this is the adjacency list for our vector. Then this is the color vector, which we will be using for identifying whether we have odd length cycles or not. Then this is the variable which is telling us whether the graph is bipartite or not. So basically, with this variable, we will identify whether there are odd length cycles or not. And then we have taken a vector component nodes, right? So basically, this vector at a certain point of time will store all the nodes which are part of a particular connected component, right? And we will apply BFS for all of the nodes which are part of this vector at a given point of time, right? Then this is our main function. So here we are receiving n and the edges, right? So first of all, we are running a for loop starting from 0 till less than equals to n. And in the color, we are pushing back 0. Basically, we have created the nodes from 0 to n, and we are assigning color 0 to all the nodes initially. And then in the adjacency list, we are pushing an empty vector right now for all the nodes, right? Then we are running a for loop for all the edges. And in the adjacency vector, what we are doing is for edge 0, we are pushing edge 1. And for edge 1, we are pushing edge 0 because this is a undirected graph, right? Then we have taken a variable max groups which will store our answer. That is the maximum number of groups in which we are splitting our graph, right? So we have initialized it with 0. And then we are running a for loop of I starting from 1 and going till n because we are running this loop for all the nodes. So they are labeled from 1 to n, right? Then inside this, we have kept a condition that if color of I is 0, only then do all these things. So why we have kept this condition is that if there were some nodes which were part of a component and we have already identified the groups for that particular component, then we do not need to visit those nodes again because that component is already done. Whatever computation we need to do for that component, that is already done. And when we would have done all of that computation for that component, at that point, we would have colored each of the node in that component, right? So if the color of a particular node is 0, so it denotes that the component of which this node is a part of, that component is being visited for the first time, or basically this node is being visited for the first time. That is why we have kept this condition, right? And then inside this, we are clearing our component nodes vector, right? Because if it is coming inside this, if this condition is true and we are coming inside this if condition, then that means this component is being taken into account for the first time. So now we will identify all the nodes which are part of this component. So before that, we are clearing this vector and we are initializing is bipartite with true. Basically, initially we are assuming that there are no odd length cycles, right? And then we are applying DFS starting with this node I, right? So basically this I denotes our starting node and this one is the color that we are giving to this particular node. So as we saw in the explanation that to the first node we were assigning the color 1, that is why we have passed 1 over here. So now in the DFS function, what are we doing is we are receiving the node, we are receiving the current color. Then in the color vector to this particular node, we are giving this current color, right? And then this particular node is being pushed into the component nodes, right? Then, whatever are the neighboring elements of this node that we are identifying with our adjacency list, and we are checking that if the neighboring node is not already colored, then we will give it a color. And what will be that color? 3 minus the current color, and then we are calling DFS for this neighboring node, right? And if it is already colored, right, then we are checking that if the color of our node, that is the current color, if it is equals to the color of the neighbor, then that means this is a odd length cycle. So in that case, we are initializing is bipartite with false, that the graph is not a bipartite graph, right? So we are not returning from here itself. Why? Because we want to store all the nodes which are part of our current connected component into this comp nodes, right? That is why we are just dating it to false and we are not returning from here, right? So now when you will come back after your DFS is completed, you will check that if the graph is not a bipartite graph, meaning there were odd length cycles, then we will return a -1 from here. right? Otherwise we will come down. So here we have taken a variable maximum component distance, right? So basically it will store that for a particular connected component, what is the maximum number of groups that we can have, right? So here in the component nodes vector, we are having all the nodes which are part of the current component, right? So we are running a for loop for all those nodes, and then for all those nodes we are calling this function get maximum distance from the node. So basically this function, what it will do is that from the source node, which is this particular node that we are passing, it will identify the distance of the farthest node with the help of BFS, right? And whatever is that distance, that will be returned from this function. And then here we are taking the max of the distance for all the nodes, right? Then whatever is that max distance, that will be the maximum number of groups that can be formed out of our current connected component. So that we are adding in our max groups variable, and at the end we are returning these max groups, right? Then if we look at the get maximum distance from node function, so here we are receiving the source node and the total number of nodes in our graph, and then we have created a distance vector over here which is of size total nodes plus 1, and initially the distance of all the nodes is -1. So this -1 will also denote that a particular node has not yet been visited if the distance is -1, right? Then since we are applying BFS, we have taken a queue. In the queue, we are pushing the source node, and as we have pushed it, we are making the distance of the source node as 1, right? So right now in our distance vector, the source node is having a distance 1 and all the other distances are -1, right? So that is the reason we are initializing our maximum distance with 1 initially, right? Then we are running a loop that while our queue does not becomes empty, take the front node from the queue and pop it. Then of this current node, identify all the neighbors, right? Now check if the distance of that neighbor is equals to -1. So it means that this node is being visited for the first time, right? So what will be its distance? Its distance will be whatever is the distance of the current node plus 1, right? So that is we are updating in the vector, and then we are pushing this neighboring node into our queue, and we have also updated the maximum distance. So maximum distance will be the max of maximum distance and the distance of this neighbor, right? And at the end we have just returned this maximum distance, right? So this is what our code is. So if we talk about the time complexity, so if you see here we are running a for loop that is 1 to n, right? Now here if you see we have kept a condition color of I equals to 0, so none of the node will be visited twice over here, right? And then here this particular for loop is running for all the nodes in a particular component, right? So this loop and this loop combined will run n time, right? And then here we are running BFS for each of the nodes, and BFS will take v plus e time, or if we are denoting the number of nodes with n, so n plus e time, right? So basically we can say that our time complexity over here will be order of n into n plus e, right? And if we talk about the space complexity, so we have taken multiple variables over here, the color vector, which is equal to the number of nodes, adjacency vector equal to the number of nodes, component nodes in the worst case could be equal to the number of nodes if there is a single connected component, right? And then we have taken a queue over here, which could also, in the worst case, store all the nodes of the graph. So that can also go till n. And then our DFS recursion call stack would also go to n. So basically, we can say that the space complexity will be order of n. So let's try to run this. So the test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.